Alright, so we've learned a couple of derivative shortcuts. In particular, we've learned shortcuts for taking the derivative of any polynomial, in fact, any power function, any function that has of the form a number times x raised to a power, raised to a number, and exponential functions, in particular, e to the x. We know the derivative of an exponential function a to the x is f prime of 0, the derivative of the function at 0 times a to the x. So let's look at some examples now. I'm just going to work through some of the book here. The ones I'm going to work through are even, and they should match up pretty well with your homework. But I encourage you to do as many examples as you can. You should try all those odd examples in, say, 3 through 23 and see if you can get the answer that's matched up in the back of the book. And you should really just practice as many derivatives as you can. One of the keys to being able to do calculus is being able to take derivatives quickly and easily and use the rules that we've talked about. Let's start with number 4. Couldn't be easier. We have f of x is the square root of 30. Doesn't matter what this number is. It's a constant. The derivative is 0. Derivative of any constant is 0. So it doesn't matter what the number is. If it's a constant, the derivative is 0. Let's take a look at another one. Number 8, we have a function h of x. It's equal to the quantity of x minus 2 times the quantity of 2x plus 3. Now, we'll actually learn a rule later to be able to handle two functions multiplied together. But for right now, what we're going to have to do is multiply this out. So let's FOIL it out. First is 2x times x, which is 2x squared. The outer 2 is 3 times x, that's 3x, and then minus 4x. For the inner two terms multiplied together. Finally, negative 2 times 3, that's a negative 6. Now, at this point, we can either combine these terms or start taking the derivative. Let's go ahead and put it in simplified form first. Let's see, 3 minus 4, that'll be a negative 1. Alright, ready to roll. Now, h of x was the original function, so we're looking for h prime of x. It's important to use the correct notation and write out what it is. H prime of x, don't just write this equals the derivative. That's not true. The derivative, in other words, what am I trying to say here? What I see a lot of times is people start taking derivatives and they'll just keep the string of equations going and take the derivative from there. That's not true. This does not equal that. This is what h of x is equal to here. Okay, now h prime of x, the derivative, what is that equal to? Well, that again is equal to 2 times the derivative of x squared, which is 2x. The derivative of a constant times a variable. The constant here is negative 1. Remember, that's just a linear portion. The slope of that line, negative x, is negative 1. So that's just going to be negative 1 there. And then the derivative of a constant, negative 6, is 0. So h prime of x is equal to 2 times 2x, or 4x, minus 1. Alright, so far so good. Let's try another one. How about... Oh, I don't know. How about I'm going to skip around here a little bit. Let's try number 14. Number 14, we have capital R of x, and it is equal to the square root of 10 divided by x to the 7th. Now, one thing you need to be able to do is you need to have a good algebraic background to be able to rewrite these functions in terms of something that you recognize that you can use a derivative rule on. In this case, I can rewrite this as the square root of 10, and instead of that over x to the 7th, I can write that as x to the negative 7th. So maybe let's put an intermediate step in there. I first recognize this is the same as this, square root of 10 times 1 over x to the 7th, and then that's the same as the square root of 10 times x to the negative 7th. Alright, once I have that, then I'm going to say my notation. Don't forget to put your notation. This is r prime of x. What's it equal to? Well, they have a constant there, so we'll just bring that constant down times the derivative of this power function, x to the negative 7th. Bring the negative 7 down, times x to the, reduce the power by 1, negative 7 minus 1, that's negative 8. So we have negative 7 times the square root of 10, x to the negative 8. So we just write it like that maybe, or maybe like this, and if we want, we could put that back in this form here. Negative 7 square root of 10 divided by x to the 8th. But again, very important you use your correct notation. When you're taking the derivative, call it the derivative. Don't just keep a string of equations going. Okay, let's try. Let's go ahead and do 16. In a nice shade of light blue. 16, we have y equals the square root of x times x minus 1. Now, what I'm going to do here is I'm going to multiply the square root of x through here. In order to do that, you may want to think, what does the square root of x mean? Rewrite that in exponential terms. That's the same as x to the 1/2 power. Always a good idea to convert your radicals to rational exponents when you're taking derivatives. So now when I take the x to the 1/2 through there, I have x to the 1/2 times x to the first. We add those exponents to get x to the 3/2. X to the 1/2 minus 1 is x to the 1/2. Now I'm going to use the difference rule along with the power rule here. Now, a couple different ways we can use notation here. One is y prime, but I'd like you to see you use more of this dy dx. It's a little more instructive. If you're given a function y equals, then we'll usually write the derivative as dy dx, the derivative of y with respect to x. Y prime works as well, and it gets the point across, but this is probably the better notation. When you start with a function just called y. Alright, so we bring the 3/2 down. So we get 3/2 x to the 3/2 minus 1, that's positive 1/2, minus x to the 1/2, bring the 1/2 down, reduce the power by 1, 1/2 minus 1 is negative 1/2. Alright, so if you want, then you can convert it back. This is 3/2 times the square root of x. X to the 1/2 is the same as the square root of x. Minus, let's see, 1/2 x to the negative 1/2. That's 1 over x to the positive 1/2. Or if you like, we could write this as 3/2 square root of x minus 1 over 2 square root of x. So if you try some of these odd ones, you may get to a point where your answer doesn't exactly look like the back of the books. Doesn't mean you have the wrong answer. It just means maybe you haven't written it and manipulated algebraically to look like the back of the books. Obviously, the original answer we got looks a lot different than this final form here. So if you get an answer that looks a little different than the back of the book, just work on it algebraically and see if you can get it to look alike. Okay, let's go ahead and look at let's go ahead and do number 25. So a little bit different thing here. Now we're given a function. We want to find the equation of the line tangent to a curve at a given point. So our curve here is y equals x to the 4th plus 2e to the x. Now we've been doing problems just like this, finding equations of lines tangent to a curve given by a function at a given point. And remember, what we had to do is first find the derivative, because what we're looking for here is the graph of this function. This point 0,2 is on that function, and if we draw the line tangent, we want to find the equation of that line. So the first thing we need to do is find the derivative. So let's go ahead and find dy dx. Now we use the sum rule here. The derivative of the power term x to the 4th, we just bring the 4 down, reduce the power by 1, plus, now 2e to the x. Remember, e stands for easy. Bring the constant down. What's the derivative of e to the x? Well, it's just e to the x. That's just that simple. Don't make it harder than it is. It's easy. Alright, now what do we want to do? We want to evaluate it at where x is equal to 0. So we need to find, this is the general form. This little function here will give you the slope of the line tangent any point on your graph. We're interested in the slope of the line tangent to the point in our graph where x is equal to 0. So remember our notation. We're going to take dy dx where x is equal to 0. And that equals 4 times 0 to the 3rd power plus 2 times e to the 0 power. And so we have 4 times 0, which is 0, plus 2 times e to the 0, which is 1. So we get 2. So the slope of our line is equal to 2. Let's go ahead and just draw a picture. I don't know what this graph looks like. Say it looks like this. We're at the point 0,2. The slope of the line, tangent, we're saying, is 2. That's what we found by taking the derivative, plugging in our x-coordinate of the point we're looking at, and it comes out to be 2. That's the slope of the line. Now, what else do we need to find the equation of a line? We need the point on the line. We have that 0, 2. So let's go ahead and we'll use point slope form. Y minus 2 equals our slope of 2. This 2 came from the y value, times x minus 0. Well, so y minus 2 is 2x. Y equals 2x plus 2. We kind of knew that one already. We knew the slope and we knew the y-intercept 0, 2. Let's go ahead and plot both the original function and this line. Let's see if we have a line tangent to our curve at 0, 2. Okay, so we got our graph here on the old wind plot. X to the 4th plus 2e to the x. Here's what the graph looks like. Now we're going to draw the line. We said it was y equals 2x plus 2. Whoops, we want to get a new equation here. So y equals 2x plus 2, and this should be tangent to our graph. You can see it is. It's a line that is tangent, touches the graph at that one point, goes in the same direction as the graph is going at that point, and touches the graph there with a slope of 2, y-intercept of 2. So we got the right answer. Alright, let's go ahead and take a look at a couple more examples. Number 37 is similar to one you'll be asked to do. We're just finding a couple of derivatives. We have f of x is x to the 4th minus 3x to the 3rd plus 16x. And we're asked to find both f prime of x and f double prime, the first and second derivatives. So remember, second derivatives, third derivatives, we can keep taking derivatives because the derivatives themselves are functions. So taking the derivative here, we have x to the fourth, so the derivative of that is 4x to the 4 minus 1 is 3. Minus the derivative of 3x to the third, leave the negative 3 there. Derivative of x to the third is, bring the 3 down, x to the 3 minus 1 is 2. This is a linear portion, a number times the variable. The derivative of the linear function is just the slope of that function, because the line tangent is the same as the line. So we get 16 for that. So let's simplify f prime first before we go on. We got 4x to the third minus 3 times 3, which is a 9x squared, plus 16. Now the second derivative is going to be f double prime. So we have our notation. So we're going to have the derivative of 4x to the third. That'll be 4 times the derivative of x to the third is 3x squared, minus 9 times the derivative of x squared, which is 2x, plus 16. 4 times 3 is 12x squared minus 18x plus 16. You can just skip right to this step, by the way. I'm just trying to be very pedantic here with the constant in front, derivative of the power term. But you can just take the 3, multiply it by the 4, and get 12x squared, and so on. So the second derivative would be 12x squared minus 18x plus 16. What if we kept going? How about the third derivative? F triple prime of x. Well, here we'd have, bring the 2 down times the 12, give me 24x. 2 minus 1 is 1. Minus, this is a linear portion, 18x, so it's just going to be a negative 18. This is a constant, so the derivative of that is 0. Let's go one more. How about the fourth derivative? Remember, we put the 4 in parentheses up there. Or you could, if you want, you could use a IV. That's a Roman numeral 4 there. But what do we get here? Well, this is a linear portion now, 24x. The derivative of that is just the constant 24, and the derivative of 18 is 0. Finally, how about the fifth derivative, or f5 of x? Well, it's just the fourth derivative is 24. The derivative of the constant is 0. So we finally got to, don't mind that, we finally got to 0. Alright, can't take any more derivatives. Well, we could. We just keep getting 0 after 0 after 0 if we kept taking derivatives. Now, just a couple notes about some of the other problems. On 43, you want to know what interval this function f of x, which is equal to 1 plus 2a to the x minus 3x, is increasing. Where is this function increasing? Well, remember, increasing function, if f of x is increasing, that's true if and only if the derivative is positive. Positive derivative means the function going up, because the derivative, remember, is the slope of the line tangent. Don't forget about the definition, what the derivative means, just because now you know how to take a shortcut. That's the number one problem we have in calculus, is that students learn their shortcut and they completely forget what the derivative means. It's the slope of the line tangent, how fast the function is increasing at that point. If that is an increasing function, the derivative is going to be positive. Alright, so if you take the derivative here, derivative of the constant is 0. Here we have 2 times e to the x, that stands for easy. Derivative is e to the x. Minus a linear term here, so we just have the constant in front. So we have 2e to the x minus 3. Where is this increasing? Well, it's going to be increasing where this thing is positive. So you would want to solve this equation, and we have done similar problems to that in previous sections. Note about 46. Where does a function have a horizontal tangent? Well, remember, we're going to have a horizontal tangent. If you consider the graph of a function, it looks like this. Where does it have a horizontal tangent? Well, here, here. What does that mean? Well, that means the slope is 0. That means the derivative is going to be 0 at that point. So what you're looking for in 46 is, where does f prime of x equals 0? So you're going to take the derivative, set it equal to 0, and solve that equation. Alright, 48, something similar. You want a tangent line parallel to the line 1 plus 3x. So that means you're looking for where your derivative is equal to the slope of the parallel line, slope of 3. Alright, let's take a look at 54 then real quick. We want to find the equations of both lines that go through the point 2, negative 3. So we want the lines that go through this point 2, negative 3, and our tangent to the parabola given by y equals x squared minus x. Well, if we look at the graph of y equals x squared minus x, Here it is, y equals x squared minus x. Now where's the point 2, negative 3? It's down here. So we're starting down at this point, and we're going to have, well, you can see there are going to be two lines that are tangent. One is going to go kind of like this, and the other one is going to sort of go and touch the graph somewhere up here, I guess. It would be more like that. So there's actually going to be two lines that are tangent to it. Let's see if I can draw a picture of it. So this is going to be the best picture. Here's a rough sketch of x squared. Let's see, is it minus x or is it plus x? It's plus x. And x squared plus x is this graph right here. We're at the point 2, negative 3. You can see there's actually going to be a couple of places where we are tangent. One is going to sort of be like that, and the other one is going to sort of be like that. This is not a very good picture here. Hope you guys are patient with me. So we're going to have something similar to that. There's actually two places of lines that go through this point 2, negative 3 and are tangent to this graph. Well, how are we going to find those points? Well, let's suppose we have some point up here. This is going to be some x, comma, y. What's y? Well, it's x squared plus x. So we're going to have a point going between from 2, negative 3 to x and x squared plus x. Now, what's the slope of this line going to be? Well, the slope is going to be, if it's tangent to this graph right here, the slope of the line is going to be f prime of x. What's f prime of x? Well, let's see, f prime, or I guess we could say dy dx. What is dy dx? Well, according to our power rule and some rule of derivatives, it's 2x plus, remember there's a 1 here, and this is a slope of a linear portion, so 2x plus 1 is our slope. So there's going to be 2 points. One is going to be up here. The other is going to be down here, x comma x squared plus x, where the slope from 2, negative 3 to this point has to equal the derivative because we want it to be tangent to the curve at this point. And the derivative is given by 2x plus 1. So the slope of this line, well, let's see, how can we find the slope? Well, one way is from the derivative. 2x plus 1 has to equal, let's see, the change in y's. So what's the slope of the line? It's from 2, negative 3 to x comma x squared plus x. Well, we'll take the change in y's, x squared plus x minus a negative 3 divided by the change in x's, x minus 2. So these slopes have to be equal. What you're going to want to do is solve this equation for x. So you're going to cross multiply here. You can think of this as over 1. And cross multiply, you're going to get a quadratic that you should be able to factor when you set it equal to 0 and solve for x. Those two values of x are going to give you your 2 points here. You find your two values for x, you'll find your 2 points. And then you can find your equations based on that. So again, solve this equation right here that you get. Your numbers might be a little bit different in your homework problem, but solve this equation for x. And once you find that x, then you're going to have the slope of your line by putting your x into this formula right here, and the point on your line. Well, actually, you already have a point on your line. It's 2, negative 3, but you can get another point on your line. X is one of your points. You're going to get 2 points when you solve this for x. You're going to get a quadratic, so you're going to get 2 solutions, which corresponds with the 2 points on your graph. So you have x comma, and then the y value is going to be your x value squared plus x, the original function. All right, and of course, if you have any questions about that, let me know. All right, and then you're going to have one similar to 62, and I think I'm going to let you guys try that on your own. And, of course, email me or get in touch with me if you have any questions. All right, you guys should be in good shape to do 3.1. You got a lot of power now with these derivative rules, so use your power wisely, always for good, not for evil. Password for your 3.1 homework is mansuetude. Mansuetude, M-A-N-S-U-E-T-U-D-E, and that, of course, means just what you would think it would mean, right? The quality of being gentle. Mansuetude. So have some mansuetude with your 3.1 homework. Let me know if you have questions.